In this lecture, we're going to talk about carboxylic acids, esters, amines, and amides. A carboxylic acid is an organic compound that contains so-called carboxyl group. You can see one right here. Carboxyl group consists of hydroxyl group here that is attached to a carbon which itself is a part of a carbonyl group. Here you can see three examples of carboxylic acids: ethanoic acid, also known as acetic acid; propanoic acid, known as propionic acid; and benzoic acid. First, we need to learn how to name those acids. In the IUPAC system of naming organic compounds, carboxylic acids are named by the replacement of the terminal E in the name of the alkane with the same number of carbons by oic acid. So methane has one carbon, and carboxylic acid that has one carbon will be methanoic acid. Ethane has two carbons. Replace E with oic acid and it becomes ethanoic acid. If carboxylic acid molecule has substituents, they are numbered from the carboxyl group. Carboxyl carbon in the carboxyl group is considered to be number 1. And then this will be number 2, 3, 4, and so forth. In this, however, in this example, the first carbon is not the carbon that belongs to the carboxylic group. It's the carbon that is first carbon attached to the carboxylic group. So the naming rules for aromatic carboxylic acids are slightly different. We're not going to focus too much on aromatic carboxylic acids, and we're going to just go with typical fatty aliphatic carboxylic acids. So here's the table showing you first for carboxylic acids: methanoic, ethanoic, propanoic, and butanoic, and the common names. Formic, interestingly enough, methanoic acid can be isolated from ants. Acidic, propionic, and butyric. So since I mentioned that formic acid can be found in ants, you literally can isolate the acid from ants. That's what irritates the skin after the ant bite. And acetic acid is the key component of vinegar and many other products that contain acetic acid. So let's take a look at the process of the naming of a carboxylic acid. Let's say we have this acid, so we need to identify first the alkane name to replace the last terminal E in the alkane name with oic acid and count from carbon 1, the carboxyl group, to number any substituents. So let's take a look at the longest chain here that contains carboxyl, and that will be 1, 2, 3, 4, and 5 carbons. So it's pentanoic acid. Now we need to number the substituent. It's going to be at the second carbon, and the substituent is methyl, so 2-methyl pentanoic acid. So next we're going to talk about the properties of carboxylic acids. Interestingly, they often used in food industry either to preserve or to enhance flavors in various soups, seasonings, and other products. For instance, sodium propionate acts as a preservative, and it's often added to bread, cheese, and other items to inhibit the microbial spoilage. Carboxylic acids have a strongly polar carboxyl group here, which contains two very, very polar groups. Hydroxyl group, which contains partially negatively charged oxygen, partially positively charged hydrogen, and carbonyl group, which contains partially positive charged carbon and partially negative charged oxygen. So you can see this layout for formic acid. This is the same layout for acetic acid. Because of those highly polar groups, carboxylic acids easily form hydrogen bonds with the molecules of water. And generally speaking, carboxylic acids that contain 1 to 4 carbon atoms in the aliphatic skeleton are very soluble in water. However, when the number of carbons goes up, the ability of carboxylic acids to dissolve in water reduces. The solubility in water is reduced. Why does it happen? If you look at this table, it shows you that even up to pentanoic acid, here, carboxylic acids are pretty soluble, but starting at hexanoic, which contains 6 carbons, and even more in benzoic acid, they become not as soluble as their counterparts. The reason for it is because the highly nonpolar alkane tail plays bigger and bigger role in regulating the solubility of carboxylic acids in water. As a matter of fact, when these tails become really long, let's say some kind of carboxylic acid with a tail that can be 15 to 16 carbons long, they will be absolutely insoluble in water. This is why they are called fatty acids. Well, one of the reasons. Carboxylic acids are weak, although they do ionize in water, and they produce carboxylate anion and hydronium cation. Why they can fairly easily lose hydrogen, why can they easily lose proton, is because the excessive negative charge can be easily stabilized in the resonance structures, and the stabilization comes from 2 oxygens in carboxylate anion, which easily absorb excessive electron density. Salts of carboxylic acids. If carboxylic acid is neutralized with a strong base, such as sodium hydroxide or potassium hydroxide, they would form the salt of carboxylic acid that can be used, as we mentioned, as preservatives or flavor enhancers. For instance, when you neutralize methanoic acid with sodium hydroxide, you will get sodium methanoate. You see how the name is formed. Ic acid, so methanoic acid, you replace OIC with O8. Benzoic acid, when it is neutralized with potassium hydroxide, will form potassium benzoate. Now, salts of carboxylic acids are ionic compounds with very strong attractive forces between ions, as any ionic compound is. They solid at room temperature, they melt at very high temperatures, and usually salts of carboxylic acids are soluble in water. So here we have 3 interesting examples that we're going to talk about in a second. Sodium propanoate or sodium propionate, sodium benzoate, and monosodium glutamate. So this is a pretty massive carboxylic acid. It's actually dicarboxylic acid anion, but we're going to talk about the roles in the food industry. So sodium propionate, previous slide on the left, it is used as the preservative in cheese and bread. Sodium benzoate is also used as a preservative that prevents the growth of microorganisms in various products that are listed here. And finally, probably the most controversial of them three is monosodium glutamate. It's a known flavor enhancer, and it is added to various products to enhance flavor. Now, a lot of people have allergic reaction to MSG by itself. Monosodium glutamate is simply a salt of a normal amino acid, glutamine. But in its salt form, people may have an adverse reaction to it. So next chapter will be about esters. In 1800s, the discovery was made that some compound called salicin, isolated from the bark of the willow tree, can reduce pain. Turns out, human body metabolizes salicin into salicylic acid, and salicylic acid in turn is quite an irritant for the stomach epithelium. So despite its pain-killing properties, salicin was really hard to use as a painkiller. The German company Bayer, chemists from that company discovered thereafter that if you form an ester of salicylic acid, it is not as irritating, but still a pretty good pain reliever. And this acetyl salicylic acid ended up what is now being called an aspirin. Esters are products of the reaction between a carboxylic acid and an alcohol. So you can see here in carboxylic acid, a hydrogen in carboxylate group is replaced with the alkane. Esters are found in all fats and all oils. They also form a basis of flavor and aroma of different fruits such as oranges or pears. Reaction of esterification is essentially the reaction of a carboxylic acid on the left and an alcohol here on the right in the presence of acid, which acts as a catalyst, and heat. So what essentially happens is hydroxyl hydrogen atom in a hydroxyl group of the carboxylic acid is replaced by an alkyl group of an alcohol. Okay, so but as a matter of fact, this whole fragment OCH3, oxygen attacks carbon and kicks out OH here. So, for instance, reaction of esterification here shown is the reaction between acetic acid and propyl alcohol. In the presence of acid and heat, this oxygen attacks carbon, replaces OH, and hydrogen goes away. So water is formed, and now you have an ester, propyl ethanoate or propyl acetate, which is responsible for the smell of pears. When we name esters, its name essentially consists of two words. The first word shows the alkyl part that comes from an alcohol. The second word is the carboxylate that comes from carboxylic acid. So for instance here, this is the part that comes from alkyl. So methyl, okay, comes from methanol. And this part comes from ethanoic acid. So carboxylate for ethanoic acid is ethanoate. So methyl ethanoate or methyl acetate. Esters, many esters have both IUPAC names and common names. For instance, ethyl ethanoate, will be ethyl acetate. Methyl propanoate, methyl propionate. And ethyl benzoate, well, there you go. So let's name some esters. Here's the ester. We need to name it. So we need to write an alkyl name for this part, and we need to write a carboxylate name for that part. So alkyl name, 2 carbons, ethyl. In terms of the acid, 3 carbons, it's propanoic acid. We change ic acid to 8 and get propanoate. So what we see here is ethyl propanoate. Turns out that many fragrances of flowers and fruits are due to esters, and usually those esters are rather small, so they're volatile, they evaporate really easily, and we can smell them. They also are soluble in water usually, so we can also taste them. So here's the table showing you some interesting esters that are responsible for flavor or odor. Propyl ethanoate that we just we didn't really discuss, it was different, but propyl ethanoate is responsible for pears. Pentyl ethanoate or pentyl acetate is responsible for the smell of bananas. Octyl ethanoate or octyl acetate is responsible for the smell of oranges. Ethyl butanoate or ethyl butyrate is responsible for the smell of pineapples, while pentyl buthanoate, pentyl butyrate, is responsible for the smell and taste of apricots. Ethyl acetate, that we already encountered before, is a pretty strong solvent which is used in various industries and at home. It is used in polish, fingernail polish, in plastics, and in various lacquers. So esters can be hydrolyzed using acid. In this case, ester, methyl ethanoate in this example, reacts with water in the presence of acid catalyst and heat. Water molecule, this hydroxyl group, attacks carbon of the ester, releasing OCH3 group, and this hydrogen completes it, forming methanol. So you can clearly see that acid hydrolysis is the reaction that is opposite to the reaction of esterification. Esters can also be hydrolyzed in base hydrolysis, so-called saponification. This is the reaction of an ester, shown here, with a strong base in the presence of heat. Strong base in this example is sodium hydroxide. So in case of methyl ethanoate, the salt of ethanoic acid, sodium ethanoate or sodium acetate, will be formed, as well as methanol or methyl alcohol. Now we're going to switch our attention to compounds that contain nitrogen, amines. One of the most famous amines in the world is indigo. You can see a couple of amino groups here, which is obtained from specific tropical plants such as Indigofera tinctoria. So we're going to learn how to write names of amines and how to distinguish primary, secondary, or tertiary amines. Amines are derivatives of NH3, which is ammonia. So hydrogen atoms in ammonia are replaced with alkyl or aromatic groups. Nitrogen atom in amines can be attached to one or more alkyl or aromatic groups. For instance, one aromatic group, 2 alkyl groups, 3 alkyl groups. Primary amines have one carbon group that is bonded to the nitrogen. Secondary amines have 2 carbon groups that are bonded to the nitrogen, and tertiary amines have 3 carbon groups bonded to the nitrogens. So this is the comparison. This is ammonia. This is methylamine. This is dimethylamine. And this is trimethylamine. So primary, secondary, tertiary amine. Simple amines are known as alkylamines. And here's some examples of naming alkylamines. Pretty easy. So alkyl groups that are bonded to the nitrogen atom are listed in the alphabetical order in front of amine. You also can use prefixes to assign them to duplicate alkyl substituents. For instance, here you have ethyl amine. This is the ethyl group. Here you have one methyl, another methyl, so dimethylamine. Here you have ethyl, dimethylamine. So let's take a look at various aromatic amines. So the amine of benzene, and it's actually a mistake here. So in this particular image, to show aniline, instead of that methyl group, there should be hydrogen. So it's a mistake on the picture. So this NH2 attached to benzene is aniline. When alkyl groups are added to nitrogen, we use the prefix N with the alkyl name. So for example, this is N, since to nitrogen, methyl aniline. When substituent is added to the benzene ring, you don't add N, you just use 3-chloroaniline. It's a dye. Well, anilines uses a dye to color different fabrics. Skeletal structures will show you the shapes of amine molecules with alkyl groups bonded to the nitrogen. So this is primary propylamine, this is secondary ethyl propylamine, and this is tertiary diethyl methylamine. Amines, since they have nitrogen, which is quite electronegative atom, they can be soluble in water. They can form hydrogen bonds with water molecules. Very similar to carboxylic acids, primary and secondary amine, which have fewer than 6 carbons, are soluble in water. Tertiary amines cannot form hydrogen bonds with each other, but they can form hydrogen bonds with the water molecules. So the bond between nitrogen and hydrogen in amines is polar. So they can form hydrogen bonds with water. Primary amines form more hydrogen bonds than secondary. Tertiary amines have no hydrogen on the nitrogen and can form only hydrogen bonds with water by using its nitrogen atom. Smaller amines are soluble because they form more hydrogen bonds with water, and the polar alkyl parts, play much less role in determining their solubility. So when you have amines with more than 6 carbon atoms, like this ethyl hexyl methyl amine, the effect of hydrogen bonding is very small because non-polar hydrocarbon chains decrease amine solubility in water. As you may remember, ammonia, primary and secondary amines, can act as Bronsted-Lowry base because the lone electron pair on the nitrogen can accept hydrogen from water, creating ammonium ion in case of ammonia, and hydroxide ion. Primary and secondary amines can do the same. They can absorb hydrogen, creating methylammonium ion and hydroxide ion. The salt of amine forms when amine reacts with an acid. For instance, you may have heard that to neutralize the fishy odor of fish, you should sprinkle it with the lemon juice. Why? Turns out that citric acid in lemon juice interacts with amines in fish and essentially gets rid of that fishy odor in fish. So this is the reaction of amine neutralization. Methylamine and dimethylamine react with hydrochloric acid, forming methyl ammonium chloride and dimethyl ammonium chloride. Some amines can be heterocyclic, such as pyrrolidine and pyrrole. In this case, nitrogen becomes a part of the ring, usually 5 or 6 atom rings. So here you can see 5 atoms, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. 4 of them are carbons, and the 5th one is nitrogen. This is why we call them heterocyclic compounds. Amides are derivatives of carboxylic acids, and in amides, nitrogen, the amino group NH2 replaces the hydroxyl group, resulting in this compound. So here's the carboxylic acid and hydroxyl group. If you replace it with amide, amino group, you get amide. So you go from ethanoic acid to ethanamide or acetamide. So amides are produced by the reaction between a carboxylic acid and ammonia, or a primary or a secondary amine. You also have to heat them up. So for instance, here you have propanoic or propionic acid, which interacts with ammonia. NH2 group replaces hydroxyl group, forming propanamide or propionamide. In this case, instead of ammonia, we use methylamine, and there's a tack on carbon, and now you have N-methyl, because this methyl is bound to nitrogen, and methyl propanamide. So the naming of amides, you drop the oic acid or ic acid, oic acid in IUPAC nomenclature, ic acid in common nomenclature. You drop this ending from the carboxylic acid name and you add the suffix amide. If there are any alkyl groups that are attached to the nitrogen of an amide, then you should name them using the prefix N, and then after that prefix you introduce the substituent alkyl name. So for instance, here, this comes from butanoic or butyric acid. This part comes from NN dimethylamine. IUPAC name will be NN dimethyl butanamide. Common name NN dimethyl butyramide. So let's take a look at the naming of amides. This amide, let's name it. So first, we need to identify the acid. The acid here is butanoic acid or butyric acid, so it will be butan amide. Now you can see that there is a methyl at the nitrogen. So now we use the prefix N, alkyl name methyl butanamide, N-methyl butanamide. Amides can be hydrolyzed by acid or base. If you use acid to hydrolyze amides, such as this ethanamide or acetamide, you will get the corresponding carboxylic acid, ethanoic acid, and the salt of ammonia, ammonium chloride, because this is a simple amino group. Now, if you have N substituted amide, like this N-methyl propanamide, and you neutralize it with sodium hydroxide, you're going to get a salt of carboxylic acid, in this case sodium propanoate, and the actual amine that was originally used to form this compound. So in this case, methanamine or methylamine. So let's take a look at the reaction. We're hydrolyzing N-methylpentanamide with sodium hydroxide. So this is N-methyl propanamide, which, so if they use pentanamides, it's a mistake. So there should be 5 carbons, but okay. So N-methylpentanamide will give us pentanoic acid, salt, sodium salt of pentanoic acid, which will be carboxylate salt, sodium pentanoate, and methanamine. So this is the concept map for this unit. Please let me know if you have any questions.